Okay, so here are the solutions to the Newton's second law practice sheet. And again, with all of these, the best practice for you is to work a question first, to try it on your own, and then to go back. And after you've tried the question, then look at the solution or listen to me go through it. So, in your own words, describe the relationship between force, mass, and acceleration. So, Newton's second law in equation form is force equals mass times acceleration. Another way I like to write that is that acceleration is force over mass. So what this tells me is that the acceleration of an object is directly proportional to the force acting on an object and indirectly or inversely proportional to the mass. That's the technical way of saying it. In my own words, forces cause acceleration, and mass resists acceleration. So if we want to draw the graph, if we look at the graph of acceleration and force between those two, I see that acceleration is directly proportional to force, or they have a linear relationship. So it's going to look like that. The more force I get, the more acceleration I get. If I double the net force on an object, I double the acceleration on an object. Done. If I look at the relationship between acceleration and mass, they're inversely proportional. What this means is the smaller my mass, the bigger my acceleration, and the bigger my mass, the smaller my acceleration. So it looks a little bit like that. Okay, so I want to find the weight of an object. Weight is the mass of an object times the acceleration due to gravity where the object is located. So, in order to find the weight of a 25 kilogram object, so the weight of mass 1 is going to be the mass, 25 kilograms, times the acceleration due to gravity, 10 meters per second squared. So it's 250 newtons. Again, forces are measured in newtons. For the next one, weight 2, we have 1.5 kilograms times 10 meters per second squared. That makes the weight of object 2 15 newtons. That's how we calculate weight. It is a calculation, not a conversion. And then for the third one, weight 3 is 115 kilograms times 10 meters per second squared. Weight 3 comes out to be 1,150 newtons. Question 3. A car has a mass of 550 kilograms. Find its weight on Earth. So that weight is mass times the acceleration due to gravity. We have the mass, 550 kilograms, times 10 meters per second squared. That makes the weight of our object 5,500 newtons. Find the net force needed to accelerate the car at 12 meters per second squared. So for this, we're going to use Newton's second law that says net force is equal to mass times acceleration. So our net force is going to be the mass, 550 kilograms, times the acceleration, 12 meters per second squared. So we just multiply those two things, and the net force comes out to be 6,600 newtons. Part C asks, if we use a net force of 2,200 newtons, what's the acceleration? So we use the same formula. Net force equals mass times acceleration. So 2,200 newtons is equal to 550 kilograms times the acceleration. We'll just divide both sides by 550. 550 crosses out, and that acceleration comes out to be 4 meters per second squared. This is an example of the type of problem that we could really expect to see with this. Number 4, same kind of thing. We have a 2,500 newton sled on Earth, and I want to know its mass. Well, 2,500 newtons is the weight. Weight's equal to mg. So 2,500 newtons is equal to mass, which we don't know, times g, which is 10 meters per second squared. So we'll divide both sides by 10. And that mass comes out to 250 kilograms. So if I take that sled to the moon, its mass is still 250 kilograms. In order to change the mass of the sled, I would have to take parts off of the sled. Unless I take parts off, I do not get a change in mass. So even though gravity is less, mass has nothing to do with gravity. But weight does. If I want the weight of the sled on the moon, sorry, we'll just write that down to reiterate. Mass only changes if the object changes. Going to the moon does not change the object, just its location. All right, so if we're on the moon and we want its weight, it's going to be mass times the acceleration due to gravity where we're at. So the weight on the moon is going to be 250 kilograms times 1.6 meters per second squared. Instead of using G for Earth, I'm going to use G for the moon. And that makes the weight 400 newtons. And then we're going to take that same object and we want to accelerate it on the moon. But since it's not asking about the weight, it doesn't really matter that we're on the moon. All that matters is the mass of the object. The net force to accelerate an object is the mass of the object times whatever acceleration we're experiencing. The mass is 250 kilograms. The acceleration is 4 meters per second squared. And so that net force comes out to be 1,000 newtons. All right, number 5, we have a sled of 45 kilograms on a frictionless lake. We want to know how to make it accelerate at 2 meters per second squared. So to get the net force acting on this object, net force is equal to mass times acceleration. We're looking for the net force. The mass is 45 kilograms, and the acceleration is 2 meters per second squared. So the net force is equal to 90 newtons. So if it does this for 3.5 seconds, how fast will it be going? How fast is a kinematics problem? So we'll go through and we'll say, okay, the acceleration is 2 meters per second squared. That's the acceleration. The time is 3.5 seconds. We start off at rest, so the initial velocity is 0. The acceleration is 2 meters per second squared. The time is 3.5 seconds, and I want to know the final velocity. The equation that has all that in there is that first one, v final equals v initial plus acceleration times time. So v final is 0 plus 2 times 3.5. So that final velocity is 7 meters per second. All right. So what we're starting to see here with these problems is that we are adding in some of that stuff that we've already done. So we have a 500 kilogram car with an initial velocity of 50 meters per second. It slows to 10 meters per second over time of 5 seconds. What's the acceleration? So to get the acceleration, we're going to have to go through and look at all the things. The initial velocity is 50 meters per second. The final velocity is 10 meters per second. The time is 5 seconds. And I want to know the acceleration. So the initial velocity is 50 meters per second. The final velocity is 10 meters per second. Time is 5 seconds, and I want to know the acceleration. All of those things are again in the first equation. So v final is v initial plus acceleration times time. So final velocity 10 is equal to 50 plus acceleration times time. So we're going to subtract 50 from both sides. So that gives me negative 40. The 50s cancel out, is equal to a times 5. So we'll just write that again. Negative 40 equals a times 5. We'll divide both sides by 5. So the 5s go away on that side. And I get that my acceleration is negative 8 meters per second squared. Now I want the net force. Well, this is what we've been talking about so far. We know that net force is equal to mass times acceleration. So net force is the mass, 500 kilograms, times the acceleration, which we just found, of negative 8 meters per second squared. Multiply those two out. And that force comes out to be negative 4,000 newtons. Now, what that negative sign means is not that we're wrong. It just means, the negative sign means the force is in the opposite direction of the velocity. Which makes sense. If you're going to take something that's moving at 50 meters per second and make it move at 10 meters per second, you are reducing the velocity. You need a force to push backwards on it. That's what that negative sign is telling us. Okay, so for number 7, we're going to do the guess method for like the whole thing. which means we're going to box every single one of our nodes. We have an 8 kilogram object, that's our mass. It has an initial velocity of 5 meters per second, that's our initial velocity. It has a net force of negative 48 newtons acting on it, that's net force for 3 seconds. That's our time. I want to know the acceleration of the object. So we're going to write down everything we know. It's more than just velocity, acceleration, and time stuff. We're now going to have mass and net force. So the mass of the object is 8 kilograms. The initial velocity of the object is 5 meters per second. The net force is negative 48 newtons, and the time is 3 seconds. So if I want the acceleration, I don't think I have enough information with the velocity and the time, but I do have enough information if I look at mass and net force. I know net force is mass times acceleration. So I'm going to plug it in. Negative 48 newtons is 8 kilograms times the acceleration. We're going to divide each side by 8, and that acceleration comes out to negative 6 meters per second squared. And again, that negative sign just tells me the acceleration is negative. We have an object that's slowing down. That's what that means. What will the velocity be after the force acts on it? So we're going to move all of our stuff down. The initial velocity is 5 meters per second. The time is 3 seconds. And the acceleration is negative 6 meters per second squared. And again, that means I have a positive velocity and the acceleration is in the opposite direction. And I want the final velocity. So, final velocity is equal to initial velocity plus acceleration times time. Final velocity is equal to 5 meters per second plus negative 6 meters per second squared times 3 seconds. So the final velocity is 5 minus 18, or negative 13 meters per second. What that tells me is that my object went forward, slowed down, stopped, and turned around. The object is now moving backwards.